So in this video we are again going to discuss some examples about generation of grammar for a given language. We are discussing it again and again as we have to introduce more and more examples so that in case of competitive exams you get more clearer concepts if you have seen more solved examples. So come, let's begin it. Now consider this example. We have to generate a grammar for this language. This language is a set of strings W such that each string W belongs to AB closure. So there is one property that number of A's are divisible by 3. That means in every string there should be the number of A's which are a multiple of 3. That is, a string may contain 3 A's, 6 A's, 9 A's, 12 A's and so on. So consider a string which have 3 A's. Now as the string is a combination of A and B, then any number of B's can exist before this A, B raised to the power m, where m is greater than equal to 0, and any number of B's can exist after this A, B raised to the power n, such that n is greater than equal to 0, and any number of A's can exist after this A, B raised to the power s, such that s is greater than equal to 0, and any number of B's can exist after this A such that B raised to the power t and t is greater than equal to 0. Now I have written greater than equal to 0. Equal to 0 means B can exist or cannot exist. Either this m can be 0, n can be 0, s can be 0, t can be 0, or all of them can be zeros. As it is A comma B closure, so as closure contains null also, 0 also, so we can have 0 B's also, but the number of A's should be divisible by 3. So this is the basic structure of our string. Now we have to generate the production rules. The production rules can be generated by first consider B raised to the power m. That means our string is starting from B. For a string to start from B, production rule like s derives bs can be introduced, and this s can again be substituted with bs, and this s can again be substituted with bs, and so on. Any number of b's can be substituted in the starting of the string using this production s derives bs. Now consider a case when m is equal to 0. Now for m should be equal to 0, then b raised to the power 0 is 1, that is the string is starting from A only. For that there should be a production rule from the start symbol s such that it derives A followed by a non-terminal capital A, such that our string is starting from this A and this whole we consider in this capital non-terminal A. Now this non-terminal A can have a production rule like, now we have reached till here. Now this A have to be substituted with this B starting with B. So A derives B, where this B is covered. Now left out is, again we can substitute any number of B's using this production because it is B raised to the power n. This can be A can be substituted recursively with BA, and any number of B's can be substituted. Now if n is equals to 0, then we do not need this B, we directly have to jump to this A. For that we can have a production rule like A. This A is followed by a B again, so A non-terminal B. Now this non-terminal B can be substituted with this B followed by this A. We need a A, so we write down capital non-terminal A, and this non-terminal A can be substituted with AB to get a terminal A of this kind. Now there are production rules like we can introduce like B derives A or AS. Using these production rules, we can terminate at this A, because if we do not need B after this A, then when t is equals to 0, the B raised to the power t does not exist, so we can terminate using B derives A. Or if our string contains 6 A's such that this whole structure is again repeated after it, then it will contain 6 A's, then B derives AS can be used, and using this S we can follow the same procedure again and we will get the whole string again after this string, and similarly recursively we can substitute AS to get any number of repetitions of this string one after the another. So when we get repetition of these string one after the another, these are 3 A's, then we get here 6 A's, 9 A's, 12 A's and so on. So by hit and trial method we have find out these production rules. Now let's test using these production rules what kind of strings are they generating. So first is S derives BS. S derives BS. Now let us say in this S we substitute this A, then we get B, A. Now in place of this A, let us say we substitute AB, B, A, B we will get. Now in place of this B, let us say we substitute this A, B, A. So now further substitution cannot take place and we have got a string BAA. You can see the string is having 3 A's, number of A's are divisible by 3 and there is only one B. So this is acceptable by this language. Consider one more example. Let us derive one more string. S derives, let us start from BS, and in place of this S, let us say we substitute again BS. BS we will get. Now in place of this S, let us say we substitute AA, A. In place of this A, let us say we substitute BA, BA. Now in place of this A, let us say we substitute AB, B. Now in place of this non-terminal B, let us say we substitute A, A. Number of A's are 1, 2 and 3. So number of A's are divisible by 3 and so this string will be acceptable by this language. So every string we have seen that are being generated using these production rules are having a minimum of 3 A's or can exceed the 3 A's in the manner 3, 6, 9 or 12. Let us consider one more example in which we get 6 A's. So let's start with S derives BS. In place of this S, suppose we substitute AA, then it will become BA and non-terminal A. Now in place of this A, let us substitute AB, B. Now in place of this B, let us substitute AS, BAS. Now in place of this S, let us substitute AA again, BAA. Now in place of this A, let us substitute BA, B and non-terminal A. Now in place of this A, let us substitute AB. Here it will become AB, B, A, Now in place of this is non-terminal B. Now in place of this B, let us substitute A, B. How many A's are there now? 1, 2, 3, 4, 5, 6. 6 A's are there. So when we were considering our previous two examples, we got 3 A's. In this example, we got 6 A's. Similarly, if we consider more elongated conversion, we may get 9 A's, 12 A's and so on. So all the A's that we are getting are divisible by 3. The number of A's are divisible by 3. They are in multiples of 3. So these production rules satisfy the language which is containing the strings a and b closure such that number of a's are divisible by 3. Now as we have proved that our production rules are correct, then let's write them in the form of a grammar. Grammar is a 4-tuple NTSP where N is non-terminal, T are terminal, S is start symbol and P are the production rules. So G is first non-terminals S, A and B. S, A, B. Terminals are small a and small b. Start symbol is S and the production rules are S derives BS or S derives AA, A derives BA or AB, or AB, and B derives BAA or AS, BAA or AS. These are the production rules and this is our grammar. So I hope so this example is now clear to you. So let's consider this example. In this you have to generate a grammar for a language such that it is a set of strings. Each string is represented by W and W belongs to the alphabet set AB. That means it is a combination of A's and B's such that W has equal number of A's and B's. That means in the string W there will be equal number of A's and equal number of B's. The order in which A and B are arranged does not matter. Only we have to keep in mind that the A's and B's should be equal in number. So it can have strings that can start from A or can start from B. String can start either from A or from B. These are the only two options. So we can have our first production rule like start symbol derives A, the string starting with A followed by a non-terminal. This non-terminal can be replaced by anything, and a string starting from B followed by a non-terminal such that this non-terminal can be replaced by anything. So this is our first most important production rule, because string can either start from A or can start from B. Now we have to write the productions for this non-terminal B and non-terminal A and B. Now suppose from the starting you have took this production S derives AB. You have taken S derives AB. So your string will be starting from A because start symbol will produce A and then non-terminal B. So your string will start from this terminal A. So this B can either be replaced with a simple terminal B and you will get a string like AB in which there will be one A and one B. Equal number of A's and B's, the property is satisfied. Or you have option that you can increase the number of B's. How you can increase the number of B's? From this production BS, you can substitute as many number of B's you want. Replace B with BS, again replace this S with AB or BA, any production you like. So recursively your number of B's will increase. Now if you increase number of B's, you will also have to increase the number of A's. Here A is only 1. So here on recursively increasing the number of B's, you have to increase the number of A's also, so that after the completion of the string, number of B's that you have introduced should be equal to number of A's, because we have to satisfy this property. So therefore we have written S here, because in this S you can get a production like AB again, so that you can bring one A together. If you substitute any property so that number of A's can also be increased in addition to number of B's, then only you will be able to satisfy this property. If you keep this A1 only and keep on increasing number of B's, it will not lead to a string that will have equal number of A's and B's. So therefore we have substituted S here so that we can introduce this production to bring more number of A's also there. Or there is one option more. You can substitute this production A, B, B. This will also help you to increase the number of A's simultaneously as you are increasing the number of B's. So this A will help you increase one more A, and recursively in this place of B you can again substitute A, B, B. So number of A's are also increasing in addition to number of B's. Then only your this equal number of A's and B's property will be satisfied. So for B we can have production like B, BS, ABB, and for A, suppose for A you have to start your string from this S derives BA. Then this A can be substituted with a terminal A, then your string will be BA, 1A, 1B, property satisfied. Or you can recursively increase the number of A's and simultaneously you increase the number of B's by using this production BA again in place of S. Or you can substitute a production like BAA where you increase the number of B's, and again recursively you can increase the number of B's by substituting BAA in this place of this A also. Or in the place of A you can again substitute this AS, and from S you will get BA. So number of A's and B's will be finally equal. So similar production will be of A also, AS, B, AA. Now let's check if we have derived all the production rules correct or not. So consider this S derives BA. We start from S derives BA. Let's say in place of A we substitute BAA. B, capital A, capital A. Now in place of this A, let us say we substitute AS. B, AS, and here also we substitute AS. Now in place of this S and this S, let us say we substitute AB. B, A, and place of S we are substituting AB. B, B. Now in place of this B and this B, let us say we substitute this terminal B only. B, A, B. Count the number of A's, 1, 2, 3, 4. Count number of B's, 1, 2, 3, 4. Equal number of A's and B's are generated. We simultaneously took any of the production starting from the start symbol, and we finally got a string that is having equal number of A's and equal number of B's. Let's check for one more string. Suppose we start from this one, S derives AB. Substitute this B using ABB, ABB. Now substitute this B using BS, AA, BS, and this B also BS. Now substitute this start symbol. This start symbol, suppose you substitute with BA only. AA, B, BA, B, BA. Now in place of this A, substitute terminal A, AA, BB, A, BB, A. Count number of A's, 1, 2, 3, 4. Count number of B's, 1, 2, 3, 4. 4 A's and 4 B's. So again we started from the start symbol production and got a simultaneously recursively putting the productions, we got a string which is having equal number of A's and equal number of B's. So every time we are starting from start symbol and we are getting in the final state equal number of A's and equal number of B's. That means our assumed productions are correct. So finally we write these productions in the form of grammar, as we have to generate the grammar for the language. So grammar is of the form NTSP. Non-terminals are SAB. Terminals are small a and small b only. S is our start symbol and P is the production rules, where P consists of these three productions, 1, 2 and 3. So I hope this example is also clear to you. So I hope so. Whatever example I have taken in this video are clear to you, and now you are fluent in generation of grammars for a given language. If you liked our video, please hit the like button, please share it with your friends, and if you have not subscribed to our channel yet, please hit the subscribe button also. And if you want to see our latest uploads and full playlist of theory and automata and computation, the links of the playlist and the video are flashed on the screen. you can check it out from there. Thank you.